morning, everyone. I don't know how to share my screen. Let's see, share my screen, 1, 2, and here we go. Is that sharing the right screen?
Yep, yep.
Very good. So what I'm going to do here is going to summarize 2, perhaps 3 projects, depending on the time I have. I know it's very squeezed for 15 minutes, but the aim of my presentation is to tell a story to those newcomers who may be using or looking to use our facilities. So I will not be focusing a lot on the results of the tests, but on the motivation and the story behind how we actually accomplish the project regarding project execution, instrumentation, safety, and so on. So let's go. Let me see this one. Yes. First of all, I'm going to describe a little bit what we did for the 7-story building test, which we tested back in 2004, the PCI parking building, and the Pier Federal Highway large bridge column. Those 3 tests are quite interesting. They have their own complexities, and they were in a way quite successful in the impact it had in the community as well. So let's begin with the 7-story building. Our shaking table was brand new. This was the first test research program that we did on our shaking table. We decided to build a 63-foot tall, slender building on the shaking table. We had no precedent about it. We were very concerned about safety, and we were able to test this in 2 phases. One involving a rectangular structural wall, and the second one involving a thin wall. So let me show you a little bit of what we did here. The motivation was to look at the performance of medium rise reinforced concrete wall buildings. We were looking at designing these buildings with lateral forces that were well below those that we could derive from the codes, and this was using a displacement-based design methodology. So we came up with this idea of a 7-story building built at full scale and tested in 2 phases. So you can see here some aspects of this building. You can see this is the rectangular wall that we tested in phase 1. There is a gap here between the rectangular wall and the flange wall. So in phase 1, we actually, the lateral resistance was provided by rectangular wall. Then we cast the gap and we tested the wall with the flange as a composite section. So we had to take several measures. This was incredibly slender. We placed some, you can see the cable, safety cables here in case that the structure will go and collapse. We rely a lot on, nobody had experienced this, not even in Japan they had ever tested a building as tall as this. So we rely on an advisory panel here. We convene a lot of people, talk about the testing and how to accomplish the test program. So it was a very slender structure. Nobody knew. It's like you are just walking into a site. Nobody had done a test this big, this tall, this slender. We knew that through quasi-static testing, we could take these walls to about 2% brief ratio, but beyond that, there was nothing, no other points, no previous testing or anything like that we could compare back. So the other thing is that the test was in very close proximity to the power plant and the control room. So if this structure were to collapse on the pump room or the control room with people in it, that will be a bad story for everyone. So we took the actions we took, and it's something that I expect if you are a newcomer or young or you have no experience, convene a group of people who have some experience, at least seniority, and have been around for some time and can foresee things that you may not be able to foresee. Get that experience from that group. So the actions that we took, we moved the control away from the pump building. We didn't want that if the building collapses, we're going to hurt anybody. We reach out to experienced professionals, senior NISU CSD leadership for guidance, and we had several meetings to check that the building could be built and tested successfully. We decided to guide the building to allow it to move towards the north, away from the pump building in case that it will collapse. The key test, the strong test, we had no spectators, nobody, no press, no nothing, for the reason that if we were going to have a bad performance, we didn't want to hurt anybody or made the news in a big, in a bad way. We had a lot of simulations done in several platforms with the PhD students, looking at possible performance, because when you have model uncertainty, you are going to get different results. So we subjected this building to 4 motions of increased intensity, and we had 3 models going in parallel with the students. At every time we test, we stopped. We looked completely at the building. It took us about 1 day to completely map the damage in the building. And at the same time, we were looking at the key test results of the building to see if we were getting things that were considered abnormal, in the sense that we're getting fairly far away from the predictions, which sometimes they do happen. And we convened the advisory panel, discussed the results with them, and compared the results with them. In the end, we tested this building to reach to about 2% roof drift ratio. The building was in reasonable good shape. It had damaged the lap splice. We could have continued, but at that point, we took the decision that that was as far as we were going to get with this building. So instrumentation, we had 600 sensors to deal with. We had accelerometers, displacement transducers, strain gauges, load cells, oil pressure transducers. So all those things, most likely you're going to have in your own test program as well. For first time ever, we use a GPS displacement sensors. Imagine how do you measure the lateral displacement in this building? You cannot put a tower that tall, and that tower actually may be excited by the shaking table itself. If you actually put it outside, you have some vibration, or you have thermal issues. So in the end, we rely on, for first time, on GPS sensors, which we co-located with accelerometers and brought the resolution down to 3 millimeters. This is still possible for tall buildings, and I recommend you to look into using GPS sensors when you're testing a tall structure. This is the test, a summary of the test. This is 2004 video. This is not so sharp as the ones we have today, but you can see yielding at the base of the wall with strains that reach about 3% and a little bit of a spot. So one of the things we did for Broadening Patch, it attracted a lot of the news. Many people was attracted, and we made the effort to attract design professionals to make sure that they could have a package of the data, students and researchers as well. With this small data set of the entire data set that we provided, I can see that people are still using and calibrating models, and can see that after 16 years, new papers come out every year dealing with the data set of this building. The other thing that we did, and is very important for you, is blind prediction. And in this blind prediction, we ask people to come up and try to, this is what we call a reasonable simple structure. Model it, we provide you with all the data. We had a web page, questions and answers, provided the data, construction drawings, whatnot. And that was a fantastic way. It was an excellent way, and I still believe it's an excellent way to reach out to the community. These are some of the results. You can see large dispersion and even errors or so in bending and overturning moment envelope in the base shear, displacements and accelerations. And I will not go into the details of this. You can see the dispersion, and that's it. And I'll move to the next project. The next project was Again, like these large projects, they come with a lot of industry collaboration and input. In this case, was a parking building, was the capstone from a multi-university, Lehigh University, University of Arizona, PI, Professor Robert Fleischman. And as here in San Diego, we tested a pretty wide building, just looking at the diaphragms, and the building was actually 3 times as wide as the shaking table. So you can see these outrigger beams providing overturning moment resistance and sliding away from the platform itself. So it was quite a complicated thing that we may not be able to do anymore on the 6th degree of freedom configuration. But the idea, this is a 40% scale building, was to test a building with walls at the ends of the building and reasonably slender diaphragms, 3 stories. And these walls here are low damage. You can see they are post-tension for low damage and repeatability. We did 16 design earthquake tests on this building. So it's again, it's a project initiated by the precast pre-stressed concrete industry with us here. Strong simulation. Again, all the testing that I've been leading has a strong simulation component during the pre and post testing stage. It's important to us to walk into this and make sure that you have used different platforms, at least for modeling your building, and gives you some degree of confidence. Nevertheless, you realize that there is always uncertainty, and you can see these uncertainty of line predictions. It's very, very difficult to nail the response of a building a priori. Again, we had significant input from industry, try to look at the design, safety, and whatnot. Let me go fast because I'm running out of time right now. So this is the motivation for this was to look into building diaphragms. They had, again, components from UCSD, University of Arizona, Lehigh University. And you can see here, the emphasis was here to take this building as far as we can. So we implemented a safety tower. You see the safety tower here. So the building could be taken to plus or minus 4% roof drift ratio. And beyond that, we were not going to take it anymore. So we had some impact members on this safety tower. We left the room there. And in the end, you can see the building here impacting the safety tower in the last test. You can see the opening there. And you can see the damage. You can see some timbers here that were crushed by the impact of the building against the safety tower. Finally, it's for Broadening Patch. This was meant to be a 2-year project, ended up being a 13-year long project with the testing, the capstone testing, working with industry, and in the end, as a group, we put prescriptive requirements that were balloted and approved for ASC 716 for the design of precast concrete buildings. In all fairness to Tara, I have another presentation here. I leave it for those of you just browse through this one. Again, it's the same concept of instrumentation, but I will stop here and basically give you a final slide or so. I think we have a unique facility in the nation here for all of you to do research. You can do it at full scale or large scale, depending on what your budget is, depending on the constraints that you have. So you can use these as culmination of a large research project. So you can have extensive simulation. You can work with other universities. You can look at what do you want to do. You want to design and check existing codes or guidelines. You want to test new retrofit, seismic retrofit strategies, come up with new innovative systems. All of those things, it's up to you to come up with the ideas and make sure that you get funding through the NSA funding process or so. I think everyone who has gained experience from the shaking table here, us here in San Diego, I can see John Vandelintis here, Robert Fleischman, Richard Stolz, many of our friends and colleagues who have tested here will be, of course, very happy to help you designing your testing, looking into basically how you can put a research plan or instrumentation, how do you execute a test. it's at the very beginning overwhelming, but if you rely on people who have the know-how, we are very happy to help you. We don't have to be copy eyes, but we are happy to help you in your proposal. So with this, I would like to say thank you and leave time for Tara.